Hi, in this video, we want to take a look at Poisson regression. Okay, so regular linear regression assumes that the residuals are normally distributed and they have an expected value of the linear equation and constant variance with independence, or excuse me, zero covariance between observations. Now, what about the situation where we don't have normally distributed residuals? Well, we want a different model structure in that situation. And so let's say that we're dealing with count data. So if I'm working with count data, the Poisson distribution is a good choice to work with. So let's look at Poisson regression. Now, I personally don't use this very often in my work. It doesn't come up very often. Usually machine learning situations work better for me in this case, but this is definitely a good tool in your tool belt to have, something to be ready to use. All right, so when do we want to use this? When I want to do regression with one target variable, and my target variable is count data. That's when we want to use Poisson regression. Okay, so let's go ahead and load some data. Actually, let me scroll up real quick. Yep, all right, that's good. So we're going to use the N minor data set from GLMS data. All right, so this is a data set of counting animals in a region. And so they're in the area, they measure some aspects of the region and they count the number, I think it's birds. I believe this is in Australia. And here are the column names. So here's the target variable, the number of birds. Now here, this is a binary vector signaling is there one or more of the species identified. Then we have numeric predictor variables, and then we have binary categorical data right there. And you'll notice as, you know, let me scroll down. So at no point do we have the double ones in this column, in these two columns. So it's always either grazed or it's shrubs or it's something else every single time. Okay, and now something I went through when I ordered the data by the variables that I believe are the most important for this. So here, this is my target variable, it's the most important. Here, this is a binary vector for the target variable. So this is the one, this is the column I would use if I wanted to use logistic regression, where is the species present, yes or no, not considering the number. Then I just looked through, I feel like this is the order for the numeric variables, their importance, and then I felt like grays was a little bit more important than shrubs when I was looking over the data before I made the video. All right, so, and you'll notice that the binary vector is 0 every single time the count is 0, and it's 1 every time the count is 1 or greater. All right, and as always, I like to have my point colors correspond to an important variable. So a good choice to do would be to have it either correspond to the count or correspond to the presence of the species, yes or no. I chose count for this video. Either way is a reasonable choice. All right, so now let's visualize the data. So here I'm going to just look at the scatter plots initially. So I'm using the pairs function to achieve this. So we're going to say that the target variable depends on these 4 numeric variables. And, you know, we can see kind of an increase. You know, like if you move this 1 point, you wouldn't see like a line here. Maybe something's going on here. And I'm not really seeing much here, but you'll notice every single time that 0 happens a lot, and that's common for Poisson regression. So because of the count aspect, a good portion of the time, there are no observations counted. Okay. And then here we can look at the scatter plots to see if there's any collinearity. I'm not too worried about collinearity in this case. All right, now let's look at box plots on the categorical binary vectors. So let's look at the count on compared to grazed. All right, so we can see that the boxes are knocking up against each other horizontally, that the median line is slicing the interquartile range. This median line is slicing the interquartile range. So here I'm leaning towards grays not being a very important predictor. All right, so let's look at shrubs. And shrubs, we can see that we have a lot of zeros when there's shrubs around, but there's not much of a distinction over here. So yeah, I'm not really feeling it on this one. All right, so now let's go ahead and start building models. All right, so what we're going to do, we are going to try to do regression on the expected value. All right, so remember, when I'm modeling in regular regression, I have a linear equation is equal to the expected value of y given x. Well, here with Poisson regression, the expected value is the rate. So we are looking at the rate given the predictor variables is what's equal to my linear equation. Okay, whenever I do generalized linear models, we're going to have something called a link function. Think of the link function as being a bridge between the distribution that I want to have for my target variable and my linear equation. The link equation is like a bridge to connect the two. All right, when we're talking about Poisson regression, we have three possibilities. We have the log link function, identity, and the square root. All right, so the log is the default, and from my experience, log is almost always the best one to choose. I would say the second best after that would be square root, and I would use square root when it looks like I don't have constant variance because of the connection with the transform that's in another regression video. And then identity, I honestly have trouble even getting identity to even run, so I don't think it's going to be useful for you, but it's a tool in your tool belt. Consider using it. So let's go ahead and build some models. So we're going to go generalized linear model function. Here I'm using the log link function, identity link function, and square root link function. Okay, so you'll notice that I've got the formula just like in regular linear regression, the data, that's normal. Now for family, so regular regression, I don't need a family distinction. The family would be Gaussian in that one. I just need, but if I want to do Poisson regression, I have to declare the family is Poisson. Okay. Now, if I'm okay with the default of log, I do not need to declare the link inside. But if I want to do something other than the default, I need to make a declaration inside here. So here I'm saying don't use default, use identity. Don't use default, use square root. Okay, so something about generalized linear models is that we don't have all the nice matrix equations that we have like for regular linear regression. In fact, we need a convergent algorithm to be able to work this. The maximum iterations is going to be something that might come into play. So what happens is that the algorithm makes an approximation on the parameters. Then it uses that approximation to try to get a better approximation. Then it looks at the data and tries to get a better approximation based off of the previous approximation. And then looks at the data and it tries to take the last approximation and get it even better. And it keeps on doing this back and forth, data, current estimate, data, current estimate, data, current estimate process over and over and over. Well, how many times is it going to do it? With the maximum number of iterations I have listed down. So here I chose 100 just because that's just a round number. Here is a good rule of thumb. If you can't get it to converge, if you start getting warning messages about it not converging, that's a sign that you have a bad model fit. So if you need to increase the maximum iterations to a very large number, be prepared for you to have crap model. Just something to watch out for. If it takes a long time for a model to converge, it's probably a bad model structure. Just something that I've observed in my personal experience. Now, I've never seen that written down anywhere, but that makes sense that if the model doesn't fit the data very well, it's going to take more time, more effort for the computer to get the best fit possible. All right, now, something about using the identity link function is that with some data, you're going to need to give it an initial starting point. So remember, when I talked about convergence a moment ago, I said it takes an approximation, looks at the data, improves the approximation. Look at the data, improve the approximation. It keeps on doing this back and forth, back and forth, back and forth. Okay, well, so sometimes we need to give it an initial approximation. All right, so what I usually do is I find values for a reasonable alternative model. I take those coefficients, those parameter estimates, and I put it in. So you'll notice that I took the coefficients from the standard Poisson regression and I put it into the identity version as the starting values. And this is, a reasonable way to go. If I didn't have, so if I was doing regression, another type of linear regression, and I needed an approximation, honestly, I'll start with standard linear regression, get those coefficients, and just slap those in, because usually those are pretty good starting points. And if you have a good model structure, usually things aren't going to vary that much. If you see big differences, there's probably a problem going on. So that's something to consider if you're looking at logistic regression with the logit link function or the probit link function, or one of the more exotic ones. All right, and here we use the square root link function. All right, now, something about link functions. If I'm working in machine learning, if I'm doing a neural network, what's the activation function is the inverse of the link function. So neural networks also have link functions, but we don't declare the link function, we declare the activation function, which is the inverse of the link. So it's something just to be mindful of. So sometimes you'll hear me talking and I'll say activation when I mean link, I'll say link when I mean activation. They're related to each other. I've never had a problem with it, but with messing it up, but it would be more professional if I kept it straight. All right, so now let's look at model diagnostics. Now, something about Poisson regression is that it's really best to use quantile residuals rather than regular residuals. Okay, so when I go through and do my initial plots, I'm going to use quantile residuals rather than regular residuals. All right, well, after I have my model, I'm going to go ahead and do a summary function and take a look at the output. So I can see that EUCs is by far the most statistically significant predictor, and area is definitely interesting. And timber is a little bit bigger p-value than we'd like for hypothesis testing. My personal opinion in real life model building is that it's okay to have one predictor that's not statistically significant. More than one, you're usually pushing the envelope on stuff. Now you'll notice that there's a lot of stuff that is not present when I do generalized linear models. For example, I don't have the ANOVA test popping out here. And I don't have an R squared. That's because everything is built up using maximum likelihood rather than the techniques of regular least squares. And you can see 6 iterations. 6 iterations is not very big. If I see a big number of iterations, I will be prone to concluding that it's not a good model. Now the other two, the identity and the square root link function models, they had a larger number of iterations. I felt that the default log link function gave the best model, so that's why we're looking at it. All right, so here we want the quantile residuals, and we're using the statmod package to get the function. And here are the FID values. So let's look at the QQ plot of the quantile residuals. And all right, things are a little bit deviating, but that's okay, not too bad. A little bit high up here. And now we want to take a look at the FID values and the residuals. And okay, so using the colors, I can see that the larger target value variable values are up top, and down here are where all my zeros are. So that might be something I need to be mindful of. That to me, it looks like I kind of have like a gradient of colors shifting this way. That's something I'll want to watch out for. I only have so much data, so I probably just gonna run with it. So let's look at our Cook's distance. Now for Cook's distance, this is kind of interesting that virtually everything is small until I get to the largest observation. All right, so I can see that the Cook's distance for my largest observation is going to be rather big. So I anticipate that that's probably going to have a lot more influence than other data points on this model. So that's something that I might want to consider getting rid of it. I might want to consider changing up some values, imputing on it to get a better fit. All right, let's look at the hat values. And once again, the hat values give a very similar story, like visually. Now scale, of course, is different, but the biggest hat value is the very last one, which has the largest target variable. Okay, so that is something that I need, so I would really want to investigate this data point before I would launch this model. Okay, so now I want to take a look at the regular old standard diagnostic plots. And we see this, the color gradient once again. So these are standard, or not standard, these are regular residuals, not the quantile ones. Now look at this dip. This dip is pretty big. So you can see here that this is a different normal plot than the other one. So this really shows you why you want to use the quantile residuals. Here we got the scale location. And that line looks relatively flat. We kind of have a line here, might want to be worried about, but these are all zero. So, I've got a clump of zeros floating around, probably going to be okay. Cook's distance, where I looked at that. Residuals and leverage. All right, so we can see that this point does have a lot of leverage on the rest of the model. I definitely would want to investigate this data point before I would include it in model fit. And once again, we see that that's pretty high up. This one's deviating also, so we would want to be mindful of it. Yeah, so this has so much leverage, it's actually like disrupting the scale of everything. So remember, we have a lot of properties of the hat matrix, and because of that, there's only so much dispersion of the points that we can get. If one point is far out, everything else has to kind of like clump up and get mushed together. So because this point is so thrown off from everything else, I'm not seeing the information inside here. Okay, that's all I've got for you. Take care and goodbye.